Okay, these are properties of von Neumann entropy. They motivate the definition of the mutual information, as in the classical case. And there are other properties that the entropy satisfies. The two most important ones are Iraqi-Lieb, which is a bound on the difference. So you get yourself a kind of a triangle inequality. And another way to write this in terms of the conditional entropy, so we saw that quantum mechanically the conditional entropy can be negative, but it can't be arbitrarily negative. It's bounded below by minus the entropy of A. And then finally, we have this inequality, strong subadditivity, which might look a little bit opaque at first. And it's also, you can, using purification. By the way, this one is related to that one by purification, to subadditivity. Iraqi-Lieb is equivalent to subadditivity by purifying AB. And this one is equivalent to same left-hand side is greater than or equal to S of A plus S of C. But let me just stick with this version. And this, if you're trying to figure out what you should take away from this, what is the meaning of this inequality, it's helpful to write it in terms of the mutual information. And it says that the mutual information between A and BC is at least that between A and B. So which makes sense. So it kind of helps to justify this claim. So a measure of correlation should have the property that the amount of correlation shouldn't decrease if I add on another subsystem. So if I adjoin C to B, the amount of correlation with A, if anything, should increase. Or I can write it in this way, in terms of the conditional entropy, and then it goes the other way, that the conditional entropy can only decrease under adjoining another system, because that gives you more information about A. Okay, so this strong subadditivity is incredibly important in quantum information theory. It kind of underlies your operational interpretations of basically all of these quantities that we're talking about. Okay, and since I talked about Renyi entropies, and by the way, I mean these properties also, as you will see, are crucial in when we discuss entanglement entropes in field theories. So that's why I'm discussing them now. Now the Renyi entropies for alpha not equal to 1 are extensive. So they obey that first line, that on a product state they add up. But they have none of the other properties. And that means, so I'll just highlight one, we can define a Renyi mutual information and people often calculate this in field theories by analogy with the mutual information. My God. And by virtue of extensivity, we know it's true that if you calculate this, and you find that it's non-zero, then you know that there are some correlations. Let me write it this way. You know it's not a product state. So you can, if you happen to be in a situation where you're having trouble calculating S, but maybe you can calculate S alpha, let's say for alpha equals 2. Or another example is experimentally in very simple cold atom systems, they can actually measure by some fancy interferometry S2. And so then you can calculate this, and so you can convince somebody that there were correlations if you find a non-zero answer. But since you don't have any of the other properties, you don't have this direction, and this is not a good quantitative measure of the amount of correlation. It doesn't satisfy any of those things, and in fact, it scales wrongly in a thermodynamic limit, so that if you have some two systems that are correlated only by their fluctuations, so they're sort of not correlated at the thermodynamic level, but they're correlated at the level of statistical fluctuations. This would happen like if you have two gases in a piston, and you have some, at some fixed temperature, and so there's a piston separating them that can move. The piston will fluctuate by some tiny, root n amount, and the mutual information in that context will be order 1. It won't be order n, where n is the number of molecules. Your entropies will be order n, and your Renyi entropies will be order n, because they're extensive. But your Renyi mutual information, and your mutual information will be order 1 because there's only an order 1 amount of correlation. But your Renyi mutual information will be order n. So what I'm saying is that if you calculate this, and I'm saying this from experience because this happened to me once, that in a holographic system where you're in a thermodynamic limit, you have a parameter n which is large, and I calculated this Renyis, and I got this huge answer in a situation where I expected to get a small answer because I knew that the amount of correlation was very small. And I got very confused until I started thinking more about the meaning of the Renyis and realized that this is completely natural. So you cannot use these as a quantitative measure of the amount of correlation. You'll get very, very misleading answers. In fact, you can get a negative answer for this. And you can get 0 when there is correlation. Okay?
What are you using for this?
Well, this direction. Okay? Okay. Any questions? Yeah.
Which is more common to get it to be like type 1 error and type 2 error?
What?
Which is more common, that you'll correctly see it non-zero if you just choose whatever for a system, or that you'll see it you'll accidentally see it zero?
Oh, I mean, it's very accidentally seeing it to be 0 would, actually somebody once asked me, okay, give me an example of something where there's correlation and it's 0. And it took me a while to, to actually, I did write one down finally. It would require quite a bit of fine tuning, but it's not hard to get it to be negative, for example. Yeah. Any other questions? Yeah. Well, that implies by switching A and B, it implies your statement. Mm-hmm. Yeah.
Sorry, I probably missed this.
Mm-hmm.
This thing that specifies for the usual mutual information, this for the Renyi entropy mutual information, the fact that if it's non-zero, then you get not different.
Well, this is true even, so this one is extensivity. So so it's the contrapositive of that top line.
No, I meant the usual mutual information, which is exactly it's the same.
Yeah. Yeah.
Oh, I see. So it's always positive in that case.
This is the same. This is the contrapositive of extensivity. Extensivity would be saying if this equals this, then this equals 0. I'm just trying to be really confusing, that's all. Yeah. Any other questions? Okay. Finally, we get to fields. Well, so what is the question? Now we're going to do field theory. And in field theory, we're used to calculating like correlation functions. So you have 2 points, operators. You calculate something like this, maybe with more higher point, as Oliver is explaining to us how to do in a holographic theory, for example. And so based on this experience, since we're used to talking about local operators, you have some points, you might ask a question like, or you might be tempted to ask a question like, how entangled are these 2 points? Or how entangled are the degrees of freedom at this point with the degrees of freedom at this point? But this is completely the wrong question, because entanglement is always something that happens between part of a system and the complement. So if I were to ask a question about just 2 points, then I would really have to sort of isolate these 2 points and talk about the subsystem, as we did with this GHZ example, where I asked this trick question about how entangled are A and B in the GHZ state, and the answer is they aren't. And so you shouldn't look at small parts, 2 small parts of a system, including a field theory, and ask how entangled they are. You should ask how entangled a region. So the question is, so given a region, how entangled, okay, is it with its complement? So I have some region A, and then all the rest of space. And so we want to quantify this by computing what we call the entanglement entropy. And so this picture, by the way, so I have some field theory defined on some space. So that thing, let's just stop and think for a second, assuming we are able to compute it, ask what it's going to depend on. So S of A is going to be a function of, well, first of all, the theory, in other words, whatever parameters enter into the theory. Coupling constants and so on. But then, of course, that's not enough. You need to know what state you're in. So often we're interested in the ground state, the vacuum, but not always. If somebody tells you they're calculating entanglement entropys and they don't say what state, they're probably talking about the vacuum. So the default here is the vacuum. Then, of course, it depends on your choice of region. So you have this enormous freedom in choosing your region. So the size and the shape. And then the other thing that we'll find is that, like many things you would compute in quantum field theory, it's UV divergent. And therefore, and we'll look at the structure of the divergence, unfortunately, it depends on your cutoff, which usually we're not so interested when we're talking about properties of a field theory in how they depend on the cutoff. We kind of want to get rid of the cutoff dependence. Okay? And so we're going to see how to extract physically meaningful cutoff independent quantities. So that's one of the main goals of research in entanglement entropy and field theories, is figuring out ways to extract physically meaningful cutoff independent quantities from this thing which should be considered a bare quantity. So this is So S of A in field theory is what we would call a bare quantity. And of course, from S of A, we can also compute, so if we're strong enough to compute S of A, and by the way, A doesn't have to be connected, so I could have, A could have different parts, and maybe I call this A and call this B, and then I can compute things like, well, from this function, I can compute, if I'm interested, conditional entropies, mutual informations, and stuff like that. Okay. Now, in the background of all of this, I'm assuming that since in the definition of the entanglement entropy that I gave, oh, let me just say one other thing, sorry. This state doesn't have to be pure a priori. I could be talking about, for example, putting the whole field theory at finite temperature. And in that case, of course, I'm not really answering this question anymore, as we discussed last time. So this is, in that case, this is more of a motivational question, and then the concrete thing we're calculating is this. And of course, we would love to compute quantities which actually measure entanglement, and that's what people try to do with this logarithmic negativity and so on. And that's a whole interesting story that I'm not going to have time to discuss. So regardless of whether the state is pure or mixed, I'm still going to be interested in calculating S of A. Okay, let me just make that clear. Now, the definition of S of A that I gave previously presumed the following decomposition. That the full Hilbert space decomposes as a tensor product. Okay? And first, let me just explain at an intuitive level why you should expect something like this. And then I'll say why this is not exactly true. Okay? But just sort of why should it be roughly true? It should be roughly true because in a local quantum field theory, you have the notion of a subalgebra of observables associated to a region. So I can take any two operators, either local operators, or they could be like Wilson loops, but as long as they're, so they could be non-local, but as long as they're entirely contained within A, and multiply them or add them, and I get another operator which is entirely contained within A. So I have a subalgebra of observables which is associated to a given spatial region, and I have a subalgebra associated to its complement, and they commute. So because we know that operators that are space-like separated commute in quantum field theory, that's one of the axioms, we know that the full subalgebra associated to A commutes with the full subalgebra associated to A complement. And the most natural way you realize that is if you just have a tensor product decomposition. So but that doesn't actually prove that you have a tensor product decomposition. And in fact, in reality, okay, so another way of thinking about it would be to say, and in fact the way the condensed matter theorists think about, for them, a quantum field theory is just a convenient long-distance description of a lattice system. And so if your space is really made up of a lattice and you have so then the full Hilbert space, so you really have some lattice points and maybe a spin at each lattice site, and then it's true that the full Hilbert space is indeed a tensor product, and any kind of regions I pick on the lattice, I'll have a tensor product decomposition. So from that intuition, just going to the lattice, it's a very natural thing. Now, if you want to insist on being in continuum quantum field theory, then this is not true. So it's only approximately true because of the operators that are on the entangling surface. So this is the entangling surface is the boundary of A. And if you really want to do continuum quantum field theory and define everything carefully, then you should be working in the framework of algebraic quantum field theory. And there you can rigorously define something called the relative entropy. Well, you can define the relative entropy regardless, but the point is that unlike the von Neumann entropy, which is not defined in the continuum because it's infinite, the relative entropy, which I'm not going to discuss, is defined in the continuum and is carefully defined and rigorously defined and so on. And of course, nobody can calculate it, but if you want nice definitions, that's where you would go. Now, this lattice story I told actually is fine for certain lattice systems, but actually it fails. Yeah.
How come you can't just have a third piece to the tensor product?
No, the structure is different. That's just not how it works. The actual structure of the Hilbert space in continuum quantum field theories is rather complicated, actually. Has to do with representations of von Neumann algebras and stuff like that. Yeah.
How should I think about this approximation?
It means that there's some correct notion of these quantities and some correct way to sew them together that gives you the full Hilbert space. So basically, I'm not answering the question. Another way to say it is that what they really deal with in algebraic quantum field theory is subalgebras and rather than Hilbert spaces. So they don't actually talk about the Hilbert space associated to a region in practice. If you're on a lattice, you might say there's no problem, but there's still a problem if you're doing a gauge theory. So even on a lattice, in a gauge theory, you have this approximate equality because the Gauss law constraint connects the inside and the outside. So if you know the electric field on the boundary here, from the point of view of the inside, that fixes the electric field in A complement on the neighboring lattice, well, edges, basically, or it constrains the electric field on the neighboring lattice edges. So even in a lattice gauge theory, now your degrees of freedom, at least your gauge degrees of freedom, are living on the links instead of the vertices, and maybe, you know, this is my entangling surface, and these are inside A, and these are outside A. The total flux entering this vertex from inside has to equal the total flux leaving the vertex on the outside, and therefore the physically allowed states do not form a tensor product. They're not independent on the inside and the outside. And so you have to take that into account. And the easiest way, this can be dealt with in various more and less careful ways, but the easiest way to deal with it is to pass to an extended Hilbert space where you just relax. So it's a larger Hilbert space where it does factorize, and you just relax the Gauss law constraint. And that basically amounts to allowing non-gauge invariant observables. But you sort of are always interested in a state which is in the physical Hilbert space. You're just embedding this physical Hilbert space in a larger Hilbert space. And then you have to ask, okay, does the answer I get depend on various arbitrary choices I make and how I do that? Okay, so that's a subject of some research, many papers on that. Okay, so those are the caveats, which I'm now, having stated, I'm just going to completely ignore from now on. Any questions? Okay. So we need some, I'm going to fall back on the lattice to get some crude estimates of the entanglement entropy. So I'm first going to do a ridiculously crude estimate, but it's helpful because I want us to gain some intuition for what it looks like. So suppose I have some Hamiltonian on this lattice, and I'm looking maybe at the ground state or something. And imagine for a second, so I have some local Hamiltonian. In this analysis, I'm not going to be very careful. So I'm going to assume that that leads to entanglement which is at least dominated by local entanglement, meaning that, roughly speaking, you have something like dimer bonds, like singlets between nearest neighbors, some sets of nearest neighbors, or something like that. Okay? Some very simple kind of state like that with just local entanglement. Okay? And then I divide this up according to some entangling surface. So I have, this is an A complement. And basically, the entropy I get, so S of A, is going to be proportional to the number of bonds broken, which is basically going to be the area of the entangling surface measured in lattice units. So unlike Oliver, I'm going to use a capital D for my space-time dimension. Sorry. Of course, it would be helpful if I got the exponent right. Okay, D equals space-time dimension of the field theory. This is the lattice spacing Okay, so what I'm trying to argue is two things. First of all, that you should expect, if there's some kind of locality, you should expect the divergent part, at least the leading divergent part, to go like the area. Okay? And so there may be and there will be subleading terms also, which I'll discuss in a second. But this would be your leading divergent piece. And what's interesting about this is two things. So you should immediately ask the question, of course, so is that a lot or a little? And from one point of view, it's a lot because it's UV divergent. It goes to infinity if I take epsilon to 0. But from another point of view, it's a little because if I were to take a random state in the Hilbert space, so just take the full Hilbert space and just pick some random state irrespective of the structure that I have here, the spatial structure, which is encoded in this local Hamiltonian, then I would get an entropy which goes like the log of the dimension of H sub A, the HA Hilbert space. So for a random state, so this would be for, let's say, the ground state. See what I said? If I don't say what state it is, I'm probably talking about the ground state. So for a random state, sorry for writing so low, SA is proportional to the log of the dimension of HA which is proportional to the volume of A in lattice spacing units, which is much, much larger. So in some sense, even though it's divergent, you should understand that we expect from locality that we have very little entanglement. Okay?
So when you say random, you mean not necessarily with local?
Right, just take your full Hilbert space and pick a state according to for example, pick an arbitrary state and then apply a Haar random unitary.
Are you keeping the Hamiltonian and just changing the state, or are you changing the Hamiltonian from the previous example?
This state doesn't know or care about the Hamiltonian. It's a random state in the full Hilbert space. It knows nothing about the physics here. Totally ignorant of the physics. So this is a totally unphysical kind of state. Okay? And it gives you a volume law amount of entanglement. Okay? Well, because typically we're only interested, you would get to a state like this or a similar state if you heated up the system to a temperature that was like the one over the lattice spacing or something. So usually we're interested in the low-lying states of a lattice system, especially if we're interested in taking the continuum limit where the thing hopefully turns into a field theory. Okay, so the field theory only represents some kind of low-lying sector of all of the states of the lattice system.
Why is the state that has tremendous entropy interesting at all? I mean, it's just up there in the sky.
It's not interesting. And so what I'm saying is that the physically interesting states have this very interesting property that they're highly unentangled. Yeah.
Sorry, could you repeat why for random state with a scale as the volume?
For a random state, for a random state, the entropy goes like the log of the dimension of the Hilbert space of A. I mean, so to justify this, just think about the Schmidt decomposition, and you're just going to have some kind of uniform distribution over all the states of A in your Schmidt decomposition, and so you're going to get something which is like log of the dimension. And what is the dimension? The dimension is the number of lattice points in A, which is the volume of A in units of the lattice spacing. Okay? Yeah.
I think part of the question is, why do you expect there to be non-local entanglement? Because then you're breaking a number of points.
So in this state, there's no bonds.
Yeah.
Right? I mean, the whole point is the difference between a state which knows something about the, this state doesn't even know that this lattice has some particular spatial structure. It's just a bunch of spins out in space that are, have no particular geometrical relation to each other. Whereas that geometrical relation is encoded in the Hamiltonian and is reflected in the ground state and the low-lying states. Yeah. Yeah, so if it's a state that's sort of a trustworthy state within the effective field theory, so it's well described by the effective field theory. I mean, if you take the effective field theory as kind of a formal object, that has some abstract Hilbert space that then defined by the fields in it, then of course there are crazy unphysical states in the effective field theory. But if you're looking at a state that's low-lying in the effective field theory, that's well described within the effective field theory, it will also have an area law entanglement. Okay, so any field theory state that's sort of physical has an area law divergent entanglement entropy. We're going to actually calculate this again in a different way in a little bit, and maybe that's just in a continuum quantum field theory that'll maybe help if you don't like lattice arguments. Yeah. Well, I mean, so I did this calculation for fixed lattice spacing, and then I'm kind of now when I talk about UV divergent, I'm kind of imagining that now we're fixing our theory, our continuum theory, and varying the lattice spacing, which is I think what you want to do. So I'm now taking epsilon to be a parameter. Oh, well, in fact, yeah, there are various details here that, because I'm just doing a crude estimate that I didn't, I mean, you could even argue about if, since the lattice breaks the rotational symmetry, this is even a little bit fake. And it's certainly if you have a non-uniform lattice, then it's fake, and so on. But still, the point that it goes like 1 over epsilon to the d minus 2 is still going to hold. Yeah. Did you have a question, Tom, or you want to make? Yeah, thank you. Okay, so let me try to improve this estimate just a tiny bit, and hopefully this discussion won't lead to more. I hope it doesn't lead to more confusion, but let's zoom in to get a slightly better estimate, or let me try to be consistent with my colors. I'm going to try to be consistent having the entangling surface in yellow. So let's zoom in on the entangling surface. Let's say it was a big smooth entangling surface, and now I have my lattice points, and I made the argument about breaking bonds. So, but let's do a picture where so I have spins that are fluctuating, and of course the entanglement comes from the fact that their fluctuations are correlated inside the wave function of the ground state. And these correlations occur on different length scales. So you have on the smallest length scale, you have just nearest neighbor spins are kind of fluctuating together. But then spins that are a little bit further apart are also fluctuating together. And so you have these kind of blocks of spins that are fluctuating together, leading to, for example, leading to non-trivial correlation functions if you take a spin here and a spin here. Okay? And when you cut it, then each kind of, and you know, and any given spin is kind of a sum of all of these effects. Okay? So you have fluctuations on these different scales, and on each scale where you have correlated fluctuations, when you cut it, it contributes to the entanglement entropy. Okay? So again, this is just a very rough estimate, but I want to claim, so you have so correlated fluctuations on scales L, on the scale L, where L goes from the lattice spacing up to the correlation length. So at the correlation length, they stop fluctuating together. And I want to claim that basically on each logarithmic scale, for each value of log L, there's some contribution to the entropy. So I want to do something like this. Integral d log L from L equals epsilon up to xi of some contribution. And that contribution on the scale L is going to be basically the area of the entangling surface. So this I'm going to call sigma. Sigma is the area of the entangling surface in units of L. So I get sigma over L to the d minus 2. Okay? Now, and of course, it shouldn't be the same for every L. There's some function of L here and so on. But if we just took this seriously and did the integral, if I did this correctly, then you get sigma over epsilon to the d minus 2, which is what we got before, minus sigma over xi to the d minus 2. Okay, so you get a term. Of course, you get your UV divergent term, but you also get a term from the correlation length. Now, in reality, there's all these terms in between also. So the real structure, and of course, you also shouldn't trust these coefficients either. In reality, it looks like this. You get all the terms you would expect that include, so d minus 3c, etc., all the way up to this one. So with higher powers of epsilon and lower powers of c, okay? And then you can also, in even dimensions, you get something like this. You get a log term. The coefficient of this one, the coefficient here, well, which sits here, I guess. So they all have some coefficients, and the coefficients are pretty much meaningless until you get to the last one. Okay, so this coefficient is cutoff independent and is universal, meaning it actually reflects the physics of the continuum field theory that you're going to. Or if this is 0, then this coefficient is. Okay, so you can extract the value. In the case that this is 0, you can extract the value of the correlation length from the entanglement entropy. Yeah? Well, you can, so I mean, one way to say it is by dimensional analysis, I need another 1 over L because the entropy is dimensionless. Another way to say it is you would kind of expect some kind of contribution, you know, so you have blocks of spin of size 2, then 4, then 8, and each of these you would kind of expect to give some equal contribution. But another way to say it, if you don't trust me, is I'm certainly allowed to do this and then have this, where this is a dimensionless. You can't stop me from writing it this way, where this is dimensionless, and this is the correct thing. This f is not constant. And then, of course, it changes this, but under some, I don't even know what assumptions on this, you get this. Plus, shape dependent. So all of this was kind of zooming in on the entangling surface. So things that only depend on sigma and not on the shape. Yeah?
So is the power in the denominator for the reverse term d minus 3?
d minus 2. And this is a c. Okay, and the shape-dependent terms, as we'll see, also include some universal ones. Okay? And it's a property in general, very useful one. The divergent terms, let me write it like this. The divergent part of S of A is an integral of local invariance. And this makes sense. I don't know of a proof of this, but in examples, this is what you see, and it certainly makes sense because we're talking about, you know, the divergent part is some UV stuff, and therefore it shouldn't be non-local, okay? And so an integral, over the entangling surface of local invariance of the entangling surface, and if you're on a curved manifold, the curvature of the manifold and whatever. And that means that you can do things like compute. That means if you compute this, where A and B are separated, so they don't share a common boundary, well, is finite and universal for separated So that's an example of something you can extract that's physically meaningful. It's a property of the field theory. It doesn't depend on your lattice or on your regularization, be it lattice or any other type of regularization. Okay? And there's other ways to extract the universal part of the entropy, for example, by taking derivatives with respect to the size, enough derivatives that you basically kill all of these terms and you're left with a finite part. So we'll see examples of that also. Okay? Yeah.
Is this fact because we're looking at a local QFT?
Yeah, I mean, this, I'm not sure what a non-local QFT is, but I'm pretty sure it would fail in a non-local QFT. So it's, yeah. It's when this fails, it's a non-local QFT. Good. Now that we've solved that deep problem of physics. Okay. So let me make another comment about the general structure. Leave this up. So if you're at finite temperature, then you also have an extensive part just due to the thermal entropy density, which is like where this is the entropy, thermal entropy density. Now, okay, so that's, I mean, I hope this is intuitively clear. This is for sufficiently large regions where you would really be able to distinguish between a volume proportional term and an area proportional term. Now, the interesting statement is that if you're in a pure excited state, you will also see a term like this. Where S of t, where t is the temperature that has the same entropy, that has the same energy density. So I should have said something. So a pure excited, if we're like in an infinite system, I mean a pure excited state that has a constant energy density, so infinite total energy. So a really excited state, okay? Okay, so, or we could be on a finite system, but something that has a constant energy density, and then you can ask what temperature has the same energy density, and what is the entropy density associated to that. And you will find that your entanglement entropy in this pure state has a term that looks just like the extensive thermal energy density, entropy density. Sometimes, sometimes not. And this is a diagnostic. So if your system obeys, this is a diagnostic of what's called ETH, eigenstate thermalization. So I'm not going to get into this, but this is one of these things. So it distinguishes versus a localizing system or integrable versus, there's a whole, I'm being very sloppy here, but basically there are systems that thermalize and systems that don't. And the question of whether a system thermalizes or doesn't a priori sounds like a question about the time dependence. I inject some energy, I'm in a pure state, I inject some energy, and I ask, and then I wait a while, and does it look like a thermal state after a while? That's a question about time dependence. And it depends very much on the dynamics, on how many conserved quantities I have, and so on. And there are roughly, very crudely, two categories, thermalizing and localizing systems. And I'm being very, very crude here. But the point I want to get to is that you can detect the difference not by looking at the time dependence, but by picking a pure excited state and looking at an entanglement entropy. And if the entanglement entropy of a region looks like the entropy of a thermal state, then the system looks like it's in a thermal state. This is a very powerful statement, actually. This is a very non-trivial that you can tell whether local observables look like they're thermal based on whether the entanglement entropy behaves as it does in a thermal state. Okay? There's a whole quite large area of research on this, trying to understand the difference between localizing and thermalizing states and their behavior. And let me just say one other thing, and then I'll take questions. You could ask, what happens to S of A if it's localizing? And the answer is, you don't get a volume term, you just get another area term. So even as you make A bigger and bigger, you don't get more and more entropy. More and more, I mean, you get more and more, but only proportional to the area of the entangling surface. And that's basically, how do you get a term like this in a pure state? So you get a term like that in a pure state because there's long-range entanglement between A and its complement. So there's entanglement even sort of between the interior degrees of freedom and the degrees of freedom out here, not just localized along the entangling surface. But in a localizing system, that's not true, and you only get an area law term no matter how big you make it. You never get an extensive volume law term. You had a question?
Yeah, so I was wondering, like, usually think of thermalization as something that, like, maybe you start in a non-thermal state and then you have some time of evolution to a thermal state. So can you distinguish if a state is not yet in a thermal state, but will thermalize basically through this, or can you, if you look at the equilibrium state, I guess. I don't know if I'm making sense, but like if you have a state that's not already thermalized, can you still tell if it okay?
Right. So let me just say a couple more words about this ETH business. The whole point of ETH is to predict the behavior under time evolution from the behavior of the eigenstates. And so eigenstates, of course, by definition, don't evolve. And the point is that if the eigenstates, the energy eigenstates, look for local observers like thermal states, this can be made precise, then the system thermalizes. Meaning for an arbitrary injection of energy, after enough time, it'll look like a thermal state. And so that's the point of this ETH stuff predates entanglement entropy. It started out being a separate thing where you just want to know which systems. ETH is like a diagnostic of thermalization. You want to know which systems satisfy ETH, which systems don't. And then it turns out that, in turn, entanglement entropy is a diagnostic of ETH. Yeah?
The diagnostic is not just that it's a volume law, but also the free.
Yes. Although actually that's a very good question. Whether it can ever happen that you have a volume, like a subleading volume law, I actually don't know. I mean, does anybody know? Well, I'm sure under some conditions, if there's a volume law, it has to have the right coefficient. Okay. Any other questions? Okay. So what I wanted to do next is a concrete and very beautiful example of a lattice system that is solvable and where you can compute very simply the entanglement entropy and see these behaviors. And unfortunately, I decided to skip it. Because I'm just not going to get to the holographic stuff. It's in the notes, which will be posted. I mean, it's really very instructive and lovely. Okay. Well, I'll give the punchline. I just can't resist. I mean, one other thing you want to diagnose so there are these very mysterious field theories that are topological field theories. They're mysterious because they don't have local operators, which is very strange for a quantum field theory. And how on earth would you even know what they only have non-local degrees of freedom, basically. And so they have, for example, if you put a topological field theory on a spatial manifold that has non-trivial topology, you get a degenerate. Well, I shouldn't even say ground state because they have identically zero Hamiltonian, but you have a non-trivial Hilbert space. So they don't have a unique state. And it's kind of a problem, like if you have a lattice model that at long distances behaves like a topological field theory, which they often do, to know which field theory you have or whether you even have a non-trivial topological field theory. And the entropy knows. So if you compute the entropy of a region, you get, so if we're in, for example, if we're in 3 dimensions, then you just get a term which is, so sigma now is the length of the entangling surface, and this entangling surface is now like a circle, or a set of circles. You get the length of that times something, which depends on the UV physics on the lattice, and then you get another finite term. And the finite term is universal, and if it's non-zero, then you have topological order. And if it's 0, then you don't have topological order. And in fact, it tells you more than that. It tells you about what kind of topological order you have. And this is really the way to know on a lattice, for a lattice system, whether you have topological order at long distances or not. And that's why it's called topological entanglement entropy. Okay, but I want to move to away from lattice systems and talk about relativistic quantum field theories. And it turns out, and so I think well, yeah, I'll mostly be just a field theory in Minkowski space. And it turns out that relativity constrains entanglement entropy in very interesting ways. And the first thing about it is the following. So now I have the notion, so let's say the board is Minkowski space, and I want space. Well, of course, I have a lot of freedom in defining what I mean by space. So basically, I can pick any kind of Cauchy slice I want. So these are all perfectly good Cauchy slices. Okay, and I can take some Cauchy slice. Let me be very boring and take one which appears in this reference frame to be at constant time. And I want to pick a region A of it. So I'm in some field theory. It's in some state. And let's work in the Heisenberg picture. So the state is not time evolving. And I have operators associated to points, or I have non-local operators also in my space-time. And now I picked some region living on some Cauchy slice. Now, what is associated to that region? Well, so I want to have associated to this some rho sub A. Again, working in the fiction that my Hilbert space now decomposes into H sub A times HA complement. And so what is rho sub A? Rho sub A basically contains the data that allows me to compute the expectation value of any operator in A. And no operators that are on the Cauchy slice, but not in A. For example, some operator out here, I cannot compute its expectation value knowing rho sub A. Or any non-local operator that includes a part that's not in A. Only any operator that's included entirely in A. So that's what I know on the Cauchy slice if I know rho sub A. But what else do I know? Well, if I have some operator up here that's off the Cauchy slice, because really, who cares about Cauchy slices? I mean, those are very arbitrary choices. So I don't want to be restricted to living on some Cauchy slice. So if I have an operator here, I can use the Heisenberg equation of motion to equate it to some operator which lives entirely on A. More precisely, any operator doesn't have to be local, but it has to be contained entirely within the domain of dependence of A. Any operator in D of A, I can, by using the equations of motion, equate to an operator in A, and therefore compute its expectation value if I know this. That means that basically rho sub A is not just the state as far as operators on A are concerned, but it's actually the state as far as all operators in D of A are concerned. So really I should write rho sub D of A. And in particular, if somebody else chose a different Cauchy slice, which had the same domain, not a different Cauchy slice, but a different A on a different Cauchy slice. So if I pick some A prime, which is such that D of A equals D of A prime, then rho sub A equals rho sub A prime, because it's exactly the same, it contains exactly the same information. I get the same expectation values on the same set of operators. Okay? So I have this. So really, as I said, really we should write rho sub D of A, but we don't. I mean, that gets awkward. We just write rho sub A, but we understand that for any A prime that has the same causal domain as A, the density matrix is the same. Okay? If you choose to work in the Schrodinger picture so that the state evolves, then the correct statement is rho sub A prime is unitarily related to rho sub A, where U is some time evolution operator that takes you between these two. These are sort of mini Cauchy slices as far as this causal domain is concerned. And this implies, as does this, that the entropies agree. Okay, so that's the first and most important fact about entanglement entropies in a relativistic field theory, that they really are functions not of the region sitting on a Cauchy slice, but of the causal domain.
What does it mean in Heisenberg picture to choose different Cauchy slice? You know, Heisenberg picture that it do not flow.
Yeah, it doesn't. In the Heisenberg picture, it really doesn't mean anything. But the reason you care, you could say, well, in the Heisenberg picture, why don't I just choose some random region of space-time or something like that? But then that's not, you see, some of these operators, there's not an algebra of observables associated to this region of space-time if I just choose some random one, because like this operator is secretly equal to something there. So, but if you have a notion of an algebra of operators associated to a causal domain of some spatial region. Any other questions? Okay, so the most important example of an entanglement entropy in a relativistic field theory is the simplest one, which is just a half space of a constant time slice. And its causal development is called Rindler space. So I choose x equals 0, and on x equals 0, I just choose a half space. So let's say x1 positive. and that's my A. And I have other directions, and it's half of the whole space. Okay? And what is the causal development of this, causal domain of this? So this is x naught. This is x naught equals 0. This is x1. And the causal domain, I guess I'm supposed to be using orange for this. So here's my D of A, and it's called Rindler space. And so we're going to find that there's an entropy, and that means that for an observer who lives entirely within D of A, is born and dies within D of A, the world appears to be in a mixed state, even if the whole space is actually in its ground state. Yeah?
The y-axis is the time direction here?
Yeah.
Shouldn't the causal domain
Up here?
down there?
Down here?
Yes. I mean, to the left, to the bottom left, not to the bottom right.
So this, so it's all the points that are causally connected to A and not to its complement. So in other words, it's any point, like a point here, for example. So the definition of the causal domain is that there's no, well, let me give, the definition of the causal domain is that the entire past or future light cone intersects only A and not its complement. Okay? Yeah.
How come you don't call it the causal range, though? You could say, what set of points is the causal domain of?
I never thought of that question. I have no idea.
And then you're like, yeah, the causal domain of A is all of the stuff.
I'll have to think about that. Okay. But I have to tell you that if you might be logically correct, but if you call it that, no one will understand what you're talking about. So just know that. I'm not trying to discourage you from inventing your own terminology, but okay. So the world is in a mixed state for those observers, and what's cool about this example, because it's so simple, is that we can actually write down the state pretty explicitly. And the way we're going to do that is by going to a Euclidean picture. So we're actually going to compute rho sub A. So we start, so compute rho sub A for rho equals the vacuum. So first we need a representation of the vacuum. We're going to do a Euclidean representation, Euclidean path integral representation of the vacuum. So given a field eigenstate, so a position, if you want position eigenstate, so I have some field theory, some fields, phi, and phi here is a function on the spatial positions. Okay? And here's my x naught Euclidean equals 0. And I want to compute the inner product here, the overlap, which is basically the wave functional. This here is the wave functional of the vacuum. And I compute it by doing a path integral on this half space, half Euclidean space-time. And I put as a boundary condition that phi at x naught Euclidean equals 0, x equals, let me call this phi naught, equals phi naught of x. So that's a boundary condition. So this state, write an equation here. this overlap, phi naught of x, with the vacuum is given by some normalization factor, I think it's a square root, path integral over all phi's of x naught x, e to the minus Euclidean action, where x naught Euclidean is negative and subject to the boundary to this boundary condition. Subject to this boundary condition. So I do a path integral over the half space, and that basically projects me onto the ground state. Okay, so I have a formula for the ground state wave functional in terms of a path integral. And then I can start manipulating it. So if I have two of these and I want the matrix element, so phi naught rho phi naught prime is given by this. So that's phi naught 0, 0, phi naught prime, which is just the product of two things. And that's 1 over z times the following path integral. This is x naught Euclidean equals 0 plus, and here equals 0 minus. And I have two disconnected regions. And here I say that phi equals phi naught prime, and here phi equals phi naught. So I'm just computing a product of two numbers by a path integral. I have this path integral with this boundary condition, this path integral with this boundary condition, and that gives me the matrix element of rho. So now I know my state in some explicit form. This is 1 over z times this picture. And now I want to trace over a complement. So now I want to trace both sides. So here's A. And I want to trace over a complement. That means that I set phi naught equal to phi naught prime in this region. And I sum over every possible field value, which is the same as just doing the path integral on this whole thing. Okay, so I've just taken these two and glued them together. So I set phi naught equal to phi naught prime on a complement, and I sum over all possible field values there, which is the same as just doing the path integral also on that set of variables. And this is equal to, not what's written here, but rather trace, sorry, this is the matrix element phi naught on A, rho A, phi naught prime A. Where now here I have phi naught A prime, phi naught A. So I have an explicit description of my reduced density matrix in a certain basis. I hope you don't mind the blackboard algebra here, but I just don't want to keep drawing the picture. So, and let me actually, okay, having said that, let me redraw the picture. What does this look like? What? Okay. Okay. So what this looks like is, let me just redraw it slightly. So basically, I've opened up this little wedge in my Euclidean space. Okay, so I made a slice in my Euclidean space along this half plane. And now, what you can see is that basically, there's another way to write this. So this thing is equal to 1 over z times e to the minus 2 pi times k, where k is Euclidean rotation generator about the entangling surface. So k performs a Euclidean rotation, and if I do a 2 pi rotation, then I go from this half plane to this half plane. So rho sub a. So now we have an explicit expression for this, and this is equal to the boost in Minkowskian space. This is the boost generator, and you can just write it down in terms of the stress tensor 0 to infinity dx1 x1 t0 0 of x naught equals 0. So it's an integral of the stress tensor multiplied by x1 over this whole half plane. Any questions? So we're going to use this now to calculate entropies and just to understand what's going on. So this is a case where we actually know the modular Hamiltonian. So this implies HA equals 2 pi k. So now we have an explicit expression for our modular Hamiltonian. Yeah? Thank you. Yeah. Integral dx2, etc. Thank you. Yeah.
So if we have some arbitrary, what will be the modular?
Huh. Figure that out, you get to write a paper. Nice try. We're going to see what we can say about that. Any other questions? Okay.